Okay, perfect. So we will start with the webinar today. Sorry. Um, so first of all, thank you so much for attending our session, our meeting. Very welcome, everyone. For today, we have our sixth webinar in this series of osmosis from papers to practice. Today we have our speaker, Dr. Amani Jemili. So just give me introduce Dr. Amani. She is a doctor in industrial engineering from the National Engineering School of Tunis in Tunisia. Currently, just sorry, we're trying to admit people now. Currently, she is a project management officer at MEDREC, where she is responsible for the technical implementation and monitoring of the laboratory power to hydrogen project under the Interregional Nets Italy-Tunisia program. So during her PhD journey, she focused on integrating biomass electricity supply chain into the Tunisian electricity mix using the osmosis model. Through that work, she have accumulated over 5 years of experience using osmosis and also produced important results and policy recommendations. These findings have been the objective of 3 peer-reviewed publications. In addition to her academic work, she has worked also as an associate researcher on the Horizon Europe project Reintegrate, focusing specifically on the development of several models for decarbonization pathways using osmosis. And finally, but not least, she is very honored of earning the Silver Proficiency Badge in Osmosis as recognition of her modeling skills. So for today, the name of the title of the presentation is Techno-economic optimization of agricultural biomass to electricity supply chain network, a case study of Tunisia. So in case that you have any questions, you are totally free to leave them in the chat. Just in that case, we can just go ahead with those questions at the end of the presentations. And otherwise, also you can just raise your hand at the end of the presentation and just speak to ask the question directly. Okay, so is that all from my side? So right now the floor is yours, Amani.
Thank you, Fernando. So hello, everyone. Thank you for attending today's meeting. Thank you, Fernando, for the introduction and for the invitation. So today I will present my paper, my research paper entitled The Techno-economic Optimization of Agriculture Biomass to Electricity Supply Chain Network, applied for a case study of Tunisia. This paper was published in the Elsevier journal, Renewable Energy Folks. This work was elaborated as part of a joint collaboration between our team at the National Engineering School of Tunis, INIT, Dr. Essia Znouda and Professor Chiheb Bouden, and also the German Biomass Research Center, DBFZ, with collaboration. It is a collaboration with Professor Walter Steiner. So the agenda for today's presentation, so I will try to go through the content of this paper. We will start by presenting the national context, so the Tunisian power sector. Then I will introduce the biomass supply chain, definition, activities, and the main challenges. And after that, I will present the methodology, biomass to electricity supply chain implementation in osmosis. And finally, I will conclude with the results, sensitivity analysis, and the main conclusions. So the current situation in the power sector in Tunisia. So Tunisia is facing an energy deficit, reaching 5.7 million ton in 2018. So the power sector in Tunisia relies on the natural gas import, mainly from Algeria, and only 30% of the total electricity mix comes from renewables. That's why Tunisia today is in a challenging situation. So Tunisia has to ensure or to enhance its energy security by setting strategies to have a sustainable and affordable electricity mix. So that's why Tunisia has established a strategy. So the Tunisian strategy is based on 5 main pillars. So we have the massive integration of renewable energy sources. The aim is to reach 35% in 2030. Also, the energy efficiency by aiming 30% in 2030. We have the subsidies rationalization, and here we mean that the subsidies coming or dedicated to the fossil fuels. And also Tunisia aims to enhance the grid infrastructure and interconnections. And also we have a strategy for the integration of green hydrogen and its derivatives. 8.3 million tons of green hydrogen in 2050. So the national strategy for the renewable energy sources, so we will target 100 megawatt of biomass by 2030. The integration of biomass is very important, given that, as you know, the other renewable sources are intermittent, and among the solutions, so biomass can play an important role in balancing energy supply and demand, specifically because the storage in batteries have high costs and also very limited capacities. So biomass can be a very good technology or resource to ensure the resilience of the electricity mix. So in this context, so Tunisia, okay, we have a target of 100 megawatt, but until now there is no real power plant, and also we don't have a real experience with the biomass technologies. That's why it's very important to understand the main challenges when integrating or implementing the biomass technologies. So that's why I will start with the definition of biomass supply chain. So here we have the raw material. So we have different feedstocks of biomass, which will undergo a transformation process to have a final product. And here we have the electricity as a product, and we have different upstream processes and different downstream processes. So this supply chain needs to be managed in the most efficient way in terms of material, monetary, and informational flows. And here we have the main activities of the supply chain. So in the biomass supply chain, we have the collection. So the raw material will be collected from different suppliers, then will be transported to the storage. And after that, we have the pretreatment. The pretreatment can have different aims. So the pretreatment can be used to reduce the volume of the biomass to enhance the transportation phase, or it can be used to enhance the efficiency of the conversion process. And after that, we have the conversion process, and here we have the final products. So here I have to mention that all these activities can be in different locations or can be in the same location. It depends on the type of feedstock and the situation. That's why we have different consideration that can be taken, that must be taken into account. So we have the biomass characteristics, the dry matter content of the biomass, the dry matter content of the biomass, the type of biomass, etc. We have the seasonality. So here we have the availability of biomass, if it is available or not. We have the storage conditions, the degradation and losses of the material, the methane potential of this type of feedstock, the conversion efficiency, and also we have the digestate treatment. That's why, as it can be seen, that the biomass supply chain is highly complex. That's why we need to optimize this supply chain through taking different decisions at different levels. It can be strategic decisions, tactical decisions, or operational decisions. And here we have some examples. So we have a decision on sourcing, which type of feedstock is the most suitable, which mode of transport to be used, how to plan the collection, the storage, the pretreatment, how the material flows is allocated through the different stages or processes in the biomass supply chain, at which location, which capacity is the most adequate, and also which technology is the most appropriate for this biomass supply chain. So that's why the research scope or the aim of this work or our paper is to identify the optimal configuration of biogas plant network. So here we will test centralized versus decentralized biogas plant network. And after that, we will evaluate the levelized cost of electricity for the biogas plant implementation in Tunisia. And I will present the adopted biomass to electricity supply chain or the considered biomass to electricity supply chain. So we have the biomass collection step. For the biomass, so we have the agriculture biomass, mainly cattle and poultry manure. Then this biomass will be transported to the biogas plant. And here we have the different, the pretreatment, anaerobic digestion, and the final conversion in the same biogas plant. The pretreatment here aims to enhance the anaerobic digestion, the efficiency of the anaerobic digestion process. And for the anaerobic digestion, so we have two products. We have the biogas and the digestate. The anaerobic digestion is a biochemical process in which the bacteria break down the matter to produce these two products. And then the biogas, which is mainly composed of methane, will be converted or burned in the combined heat and power, and then we will produce the electricity. So the main assumptions in this work, so will not have no storage, also no matter loss and degradation, and no heat recovery. And we will consider a co-digestion, so more than one raw material will be used. And here we have the cattle and the poultry manure. For the consideration, so in this study, it's a multi-period, multi-region, and multi-product. We will take into account the feedstock seasonal availability. Also, we will take the technical considerations. And in the next slide, I will explain this technical specifications. And this study will be applied to the Tunisian case study. And here, why OSeMOSYS for this research? So the open source energy modeling system was chosen for this work because of its high flexibility. So OSeMOSYS, in OSeMOSYS, so we can model different types of supply of energy supply chains. and also for its adaptability. And here, because our research project is to optimize the biomass supply chain and then integrate this biomass supply chain into the Tunisian electricity mix. So here, based on this model will be soft linked to another model in order to study the impact of the integration of biomass supply chain into the Tunisian electricity mix. And now we'll move to the methodology adopted for this work. So the location problem formulation. The biomass here can be collected from different suppliers in the same zone, zone G, and then transported to a collection point, and this collection point will be in the same zone with an average distance of 20 kilometers. Then we will give the model the possibility to choose between treating this feedstock or this manure in the same biogas in the same location of biogas plant, or transport this feedstock or this raw material to another biogas plant. And here we will take into account the real distance. So the main decisions here, so we have the configuration, local decentralized versus centralized network. So we will decide on the location of the manual biogas plants and also the capacities. And also we will have a planning of the amount of manure to be collected and transported for each period. And finally, we will have the electricity production in each biogas plant for each period. And this formulation was introduced in OSeMOSYS in this way through the reference energy system. And here we have just a simplified representation of only two zones. So here we have the two types of the feedstock in the same zone. Then this feedstock will be collected and transported to the collection point. And then we will give the model the possibility to choose between treating it in the same zone or transporting it to another zone. So here, if we have this biogas plant or this biogas plant. And when modeling the biomass to electricity supply chain in OSeMOSYS, it was very crucial to relate the parameters of the manure electricity supply chain to the corresponding parameters in OSeMOSYS, because it's important to mention that when dealing with the biomass supply chain, it's important to take into account the energy and the mass balances. So here, for example, when we consider the dry matter content of each type of manure and water content and conversion factor to biogas, it has been introduced through the input activity ratio and the output activity ratio. And also the model considers the seasonal variation in manure availability and the fluctuation in manure prices. And for the technical specifications, so for the anaerobic digestion process, so we consider the dry matter content for each feedstock and the water content and the methane yield for each type of feedstock. For the model inputs and outputs, so here we introduce the demand for the supply side characteristics. So we have the raw material potential and availability. Also, we have the supply side costs, and here we have the variable cost of the raw materials, and also the costs of transportation. For the techno-economic characteristics, so we have the operational lifetime, the efficiency, the capacity factor, capital fixed variable cost, and all of these parameters are related to the biogas plant itself. For the data sources, so we conducted on-site investigation, specifically for the raw material potential, the seasonal availability, and all the logistics aspects, mainly the transportation phase. And also we have used institutional and strategic reports from IRENA and other governmental sources, and some scientific papers. For the model output, so we will have the final methane production or the final biogas production, and also the electricity production, the biogas plant network configuration, the installed capacity, the material flow allocation, and finally the LCOE, the levelized cost of electricity. So for the assumptions and boundaries for osmosis, so the time domain, it's from 2020 to 2050. We divided Tunisia into 6 regions with 24 governorates. And here we mean for one region, we will have different governorates, which presented the zones, as explained before. For the time slices, so we have 2 seasons. Season 1, the harvesting season, and the season 2, the planting season. And the availability of biomass and the prices of biomass depend strongly on this on seasons. For the electricity demand, so we have introduced a demand limit to ensure the fully utilization of the available resources. For the existing technologies, so as explained before, so we have the feedstock, the collection, transportation, pretreatment, the anaerobic digestion, and combined heat and power. And our target in this model is to maximize the electricity production from biogas or from the introduced raw material. And here we impose the existing potential or rates of cattle and poultry manure in each governorate, in each region, and this is through at the entrance of the digester. For the manure available potential, so we did a forecast based on the existing data. So now we will present the results and the sensitivity analysis. So the first result is the capacity shares and the configuration. So regional centralized versus local governorate decentralized biogas plants, biogas plant network. And here in the results for the 6 regions, so we have 2 types of results. Some regions with the optimal configuration of a decentralized network, like this region. So in each governorate will treats the raw material in the same governorate. And this is mainly due to the high transportation costs. In other region, like region 3, so the model decided to centralize the biogas plants in only 2 zones. And this is mainly due to the availability of biomass or the feedstock in this region, and also the downward trend of the manure potential, which has affected the digester efficiency. And as the model has to maximize the biogas production, so the decision was to centralize the biogas plants in only 2 governorates. For the electricity production, so throughout the country, so it's an upward production, which means that the proposed network is long-term, has a long-term viability. So this type of feedstock can ensure a constant production from 2020 to 2050. And for the main results, so we have the centralized versus local decentralized network. And here in the map, so we have the different locations of the biogas plants. And here, as it can be noted, so we have a coastal in the coastal governorate. So we have the highest capacities of biogas plants, and in this region, for example, we have the it is the region 3, and here we have the the decision of centralization. Okay, and here we have also, as a result, we have the total installed capacity that can be reached from this network. It's 76 megawatt. For the LCOE ranges between $0.14 per kilowatt hour and $0.19 per kilowatt hour. And for this type of raw materials, cattle and poultry manure, so more than 70% of the target set by the Tunisian national strategy can be reached by 2030. And now we have the sensitivity analysis. So in this research work, we have conducted a sensitivity analysis, and this is mainly due to the uncertainty regarding the actual transportation distances between manure suppliers and collection points, because it's a fixed distance. That's why we need to conduct a sensitivity analysis on these parameters to see the impacts on the decisions and the different results. And also we have the uncertainty related to some costs, like capital costs of the biogas plant, which can be in the future, which can have a cost decline in the future. So that's why we did a variation of transportation distance from 10 kilometer to 50 kilometer. And also we did a variation of the capital cost of the biogas plants. So for the modeling results on the configuration, if it is centralized or decentralized, there is no impact on the decision, but there is an impact on the LCOE. So when the distance decrease, the LCOE decrease, and also when the capital cost increase, when the capital cost decrease, also the LCOE decrease. And finally, this work can be enhanced by using different types of feedstock. We can use the same approach to introduce other types of biomass. This model can be used for other countries. Also, we can add the heat production to enhance the LCOE, and also we can adopt a multi-objective optimization in which we can include the environmental, social, and economic criteria. And in this way, we can have a trade-off between all this criteria to have the most sustainable biomass supply chain. And also this model can be enhanced by using JES database if we can conduct if we can conduct a data collection on the location of the raw material, which can enhance the results of the model. And this is all from my side. So thank you for your attention.
Perfect. Thank you. So sorry, I have a kind of a cough. Thank you so much, Amani, for this presentation. So now just let me check if we have any questions on our chat. No, it looks like no, there is no questions in the chat. So now, for all our attendants, now I can open the Q&A um, part of this meeting. So just in case that any of you have a question, a doubt, a comment, feedback, or whatever that you want to mention regarding the presentation that Amani just showed us. Uh, Good. We have one question in our chat. Suman Moore is asking, can we use this model for solid waste from a city?
Um, so what do you mean by solid waste?
Suman, I don't know if maybe you want to open your microphone and just ask the question directly and elaborate a little more on what you want to know.
Hi. I just
Hi.
want to know that if we can use this model for the organic waste which is being generated from the kitchen.
Yes, yes, yes.
So,
Yes, this model can be used for the waste from households, uh, but we just need to have the characteristics of this biomass, of this type of biomass, and then it can be introduced. Uh, it can be introduced to the model. Yes.
okay, thank you.
Perfect. Chris, go ahead. Chris Manuel, can you please open your microphone?
Okay. Okay. Thank you, Fernando, and also thanks for Amani. This is a very, very wonderful presentation. Uh,
Thank you.
I'm short of words because it has come at the point where me and my colleague we are thinking in the same line because we want to take this kind of work so that maybe we can in the end produce a paper uh, through the boot camp. So with this work that has been presented, it's directly speak to the national policy of Zambia. Because at the moment, Zambia is pushing so much for non-hydro renewables. So with this kind of work, and then looking at the potential for Zambia in terms of the feedstock and this type of a model, it's a fantastic thing to witness. The one question that I wanted to ask is mm, maybe this can go even to Fernando. I've also seen Lakia is we are working uh, on the scenario development. We want to integrate the results of OSeMOSYS and the cruise model. Now the where we want to push in the non-renewable such as the wind and also the biomass. Now the target scenario is they are saying that by 2030 by 2030 we should have 33% of these the variable renewables as well as the biomass which is more stable. So now I'm finding difficult to work out which the parameters that I need to manipulate so that we can have these wonderful results that can speak to the reality. Yeah, I think
Uh,
that's and then the second part is that I also wanted to find out from Amani if it's possible or if this paper is open for the public. I would really appreciate if that's possible. Thank you.
Uh, the paper is not publicly available, but I can send the paper to you at any moment. You are welcome.
yeah, maybe regarding that last point of the paper, if you can maybe type your email in the chat, Amani, and then for example, Chris
Okay.
can can send you just a
contact me.
kind email saying, "Hi, Amani, I'm interested in getting your paper," and then you can send him. And also for everyone, if maybe you want to contact Amani and getting the paper directly, that would be fine. Um, Sorry, just to re-add on the previous question about like if I understood correctly that you want to represent an scenario of 30% of renewables, including biomass, and then you want to know which parameters you should uh, use for doing that. Is that the question, Chris? Chris, are you there? Okay. Okay, just in the meantime, we have another question, Amani, from
Yes.
Queen. What kind of your feedstock of biomass? So forestry waste, alga, agriculture residues. So maybe
Okay.
the,
For the feedstock used in this paper or in my research work, it's agriculture biomass. It's from the animal waste. It's cattle and poultry manure.
okay, perfect. Thank you.
But
Um,
the model can be used for any type of organic waste. I just have to mention this.
Good, perfect. Um, Excellent. So, any questions, additional questions regarding the Amani's presentation? No. Good. Maybe I have one final question for you, Amani. Is like,
Yes, yes,
um,
I'm
sorry,
trying to.
I'm not sure if I have a delay or it's just a glitch. So, are you
Glitch.
hearing me? Are you hearing me well?
Yes, yes.
Okay, yeah. Sorry. Just the final question from my side would be, um, uh, you mentioned that one of the opportunities for further research would be like heat recovery, right? So sorry, I don't know, maybe I missed the key explanation about that part. But my question is, if you decide to go with the modeling of heat recovery, which is the potential use of that heat in the let's say in the energy system for Tunisia, because let's consider that if you are able to use heat, obviously because you are using like a CHP unit, let's say
Yes.
that with heat recovery in the equation, it would be like, let's say, additional income for like the provision of one additional fuel. So yeah, so I just want to know maybe if you are thinking ahead in terms of heat recovery, which would be like the kind of setting for using that heat.
Okay, so for the heat production, because we have adopted the combined heat and power system, so we have as product we have the electricity and we have another co-product which is the heat. So if we have to optimize the all the product or the production, so we have to consider or to consider this heat. But for the moment, in the Tunisian context, there is no clear application or for this heat or use for this heat. But in the future, so we can think if we are using the agriculture waste, which is the animal waste, cattle and poultry, that like the resources I am using in my work. So it will be good to think about the cooling or the heating of the places where the animals are. So it can be a good application or a good use for this heat.
Thank you, Amani, for your answer. Yeah, Chris, do you want to speak now?
Okay, yes, sorry, I lost the connection. We are having bad internet. Yeah, so yeah, exactly the way you pointed it out, because we are learning the model, I think a week ago. So we want to see the situation where by 2030, we see the representation of this variable renewable. By 2030, we have a representation of about 33% of the variable renewable energy.
One question: are you working with Muio or are you working with Klitzen, or are you working
We are
with?
no, we are working with Muyo.
Good. So, if you're working with Muio, in that case, you have one feature in the, let's say, in the configuration tab, you have like one option that is called constraints, right? So the constraints is like that part that is named as user-defined constraints. So if you go there and check that, but I would say that maybe just let me share the maybe the read the docs for you to understand a little better what I'm talking about. Okay, just to say the following is that if you are using Amuio, that part that is like the user defined constraints, you have the option to set. Let's say that is not quite easy to explain here. But essentially, are you familiar with the user defined constraints or no?
Or maybe maybe we not take much of the time. I don't know if there's some documentation so that I can look at them. Then if I have further question, then I get back so that we don't take people's time. Is that fine?
Just if you want it, maybe just send me an email and I can share with you like a kind of an example of on how to do it. Because let's say that there is no like public documentation with the
Okay.
specific example of how to do it. But let's say that I can prepare something very quick and just send you like an example on how to do it.
Okay. Thank you, Fernando. Thank you.
Good, perfect, that's fine.
Yeah, because this is going
Excellent.
to be. Okay.
Yep.
Yeah, so sorry to cut you. I was saying that this is going to be very important, especially if we look at the aspect of the biomass, because we have so much potential. So it will be helpful.
Yeah.
Thank you.
Good. Thank you, Chris. Good. Do we have any additional questions or doubts for Amani? Okay, in the chat, that's nothing else. Then I don't see any additional hand up. Okay, perfect. So, considering this, thank you so much, Amani, for this presentation. Thank you for accepting this invitation in order to showcase the work that you have performed in Tunisia. Thank you so much for your kindness and willingness for being here. And also, thank you so much, everyone, for attending today and being involved in this kind of of events that we are trying to promote from CCG in terms of our energy community, energy modeling community. And just stay connected with our network on LinkedIn and also via email. And I hope to see you in a next event with us. So thank you so much, everyone, and have a beautiful day.
Thank you. Thank you, Fernando.
Thank you. Bye
Thank
bye.
you.
Bye bye.
Thank you, Amani. Bye bye.
Thank you. Bye bye. Thank you.
Bye bye.